You're sitting there right now feeling it. Gravity. It's pushing you into your chair, pulling your arms down, keeping your coffee in its mug. You've felt it every moment of your life. From the moment you were born, gravity has been your ever-present companion. It's constant, relentless, inescapable. It's just there. You don't even think about it anymore, do you? It's so ingrained in your life that your brain files it away as normal and moves on. It's the same way you don't think about breathing. It's automatic. But what if I told you gravity isn't what you think it is? What if the sensation you felt your whole life, that constant downward pull, isn't actually what's happening? Think about it for a second. You're sitting on a rock, hurling through space at an incredible 67,000 miles per hour. And yet, you're stuck to it. You're not strapped down, glued or tethered to it by anything tangible. There's no rope, no spring, no hand pushing you down. And yet, here you are, stuck to the ground. You can't float away. You can't even jump without being dragged back. There's something invisible keeping you grounded, but what is it? What's doing the pulling? What's the mechanism? Now here's the uncomfortable truth. What if I told you gravity doesn't pull at all? What if everything you thought you knew about gravity, about masses attracting each other across space, some invisible force reaching out and yanking things together, was completely wrong? What if gravity is something else entirely, something far stranger and more complex than you ever imagined? Let me show you. Newton's discovery of gravity is what most people think of when they think of gravity, an invisible force that attracts masses to one another. And that's how the story went for centuries. You drop an apple, it falls. Masses attract each other. Big mass, strong pull. Smaller mass, weaker pull. Seems simple enough, right? But here's the kicker. Newton's idea wasn't a full explanation. He knew how gravity worked, but he had no idea what gravity actually was. He could predict the path of a falling apple or the motion of the moon with extraordinary accuracy. He had the math down to a science. But when it came to explaining why masses attract, he was at a loss. Newton admitted he didn't know. He called it action at a distance and said it was philosophically absurd. He didn't understand how something could exert a force over empty space, and for centuries after Newton, we had the equations that worked perfectly. We sent rockets to the moon and built satellites with them. But we had no idea what was actually happening when gravity was at work. In the 20th century, Einstein took a different approach, and he gave us something far stranger and more mind-bending than anything Newton could have imagined. Einstein didn't just ask why things fall. He asked what gravity feels like. And that's when everything started to change. His discovery, known as the equivalence principle, was the breakthrough. He asked, what if gravity is not a force at all? What if it's something else entirely? Something that is not acting on objects from a distance, but is actually built into the very fabric of space and time itself? And here's where things start to get really weird. Einstein realized that gravity might not be a force at all, but something far more subtle, something embedded in the very fabric of space itself. He proposed a thought experiment that would change everything. Imagine you're standing in a sealed box with no windows, no way to see outside. You feel your feet pressed against the floor. You drop a ball and it falls. You feel weight. It all feels normal. But then Einstein asked a simple but profound question. Are you standing on Earth feeling gravity? Or are you in a rocket ship far out in space, accelerating upward at 9.8 meters per second squared, with the floor pushing up against you? Here's the kicker. You can't tell the difference. There's no experiment you could perform in that sealed box to figure out whether you're on Earth or in a rocket accelerating through empty space. Drop a ball, and it falls the same way. Jump, you land the same way. Stand on a scale, it reads the same. The experiences are identical no matter what situation you're in. This realization was profound, and it led to the equivalence principle. Gravity and acceleration are indistinguishable. They feel the same, act the same, and in every way are the same. If you can't tell the difference between gravity and acceleration, maybe they're not just similar. Maybe they're the same thing. This idea, which at first seemed counterintuitive, was a key moment in Einstein's thinking. It led him to rethink gravity completely. What if gravity wasn't a force pulling you down at all? What if it was something else? What if it wasn't about mass pulling mass, but about the geometry of space itself? And that's where Einstein's mind truly broke new ground. He began to see that gravity isn't a force at all. It's the curvature of space-time. Now, let that idea sit for a second. The idea that gravity isn't a force at all, but rather the shape of the space you're moving through. It's a deep shift in how we think about the universe. You see, the conventional view of gravity is simple. There's a force that attracts objects, a force that pulls them down. But Einstein said, no. Gravity isn't pulling you. Instead, mass bends the fabric of space-time. When you stand on Earth, space-time is curved around you, and that curvature guides your motion, your natural path, which is called a geodesic. Imagine this. Space-time is like a four-dimensional grid, 3 dimensions of space and 1 of time. This grid is uniform and flat when it's far from any mass. Objects that move through this flat space move in straight lines. There's no bending, no curves. Now, let's place something massive, like a planet, on that grid. What happens? The grid bends, it distorts, and as it does, everything else moving through it follows the curves. This is the key. The Earth is not pulling you toward it. You're just following the curved path laid out by space-time. The fall isn't really a fall at all. You're not being tugged toward the ground by some mysterious force. You're just following the shape of space-time itself. The Earth curves space-time in such a way that your path through it leads toward the center of the planet. But crucially, you're still just moving straight. You're following the straightest path through curved space-time. Now, this is where your intuition is going to get flipped completely. You think you're standing still on the ground, that you're resisting gravity, that you're stuck to Earth. But no, you're actually being pushed away from your natural path. You're being prevented from following your geodesic, the straight path through space-time, because the ground is in the way. The floor beneath you is pushing upward, not gravity pulling you down. It's the electromagnetic forces from the floor pushing up on you, stopping you from falling toward the center of the Earth. So when you feel weight, what you're actually feeling is a force resisting your natural motion, a force that is keeping you stationary, preventing you from falling. And if you think this is strange, think about astronauts on the International Space Station. They seem weightless, don't they? You'd think that means they've escaped gravity, but that's not true. The ISS is only about 250 miles above the Earth's surface. Gravity there is almost as strong as it is on the ground, about 90% as strong. So why do astronauts float? They're not escaping gravity. They're falling, constantly falling toward Earth. But they're moving sideways at such a high speed that they keep missing the Earth. That's what an orbit is, falling forever, without ever hitting the ground. So astronauts in the space station feel no gravity, because they're falling in exactly the same way that an object falls when you drop it. They're not defying gravity, they're obeying it perfectly. Now let's flip this around and think about what it really means when we talk about gravity. You're standing on the ground, and it feels like you're being pulled toward the Earth, right? You're standing still, resisting gravity's pull. But if you're honest with yourself, you should realize this isn't what's actually happening. You're not standing still in some fixed position. You're being prevented from following your natural path through space-time. Your feet are pressed against the floor, and that's what's keeping you from falling toward the center of the Earth. This insight completely changes how we think about gravity. It turns out that falling is the natural state. Standing still, in fact, requires force. The ball you drop isn't being forced to fall. You're the one being forced to stay in place. Your body is in a state of constant acceleration. The sensation you call weight is nothing more than a resistance to that natural motion. When you're standing, you are actively resisting the curve of space-time. Your body is trying to follow its geodesic, but the ground is preventing it from doing so. That's what weight is. It's the resistance to your natural trajectory. When you sit down, lie down, or even when you jump, you're still in this constant state of resistance. You feel weight because of the electromagnetic forces holding you in place. Now think about astronauts again. They're in free fall, but they don't feel the effects of gravity, even though gravity is still there. Why? because they're not being stopped by anything. They are free to follow the curved path of space-time. In free fall, there's nothing interfering with their motion, so they don't experience weight. They are moving along the geodesic of space-time, following the natural curvature, which results in their weightlessness. So, astronauts aren't escaping gravity. They're simply in a state where they are allowed to follow the natural curve of space-time without anything in the way. But here's where it gets even stranger. You might ask, if gravity is just the curvature of space-time, then why does mass curve space-time in the first place? Well, that's the question that takes us to the deepest part of physics, and honestly, we don't have the answer yet. Einstein's equations describe how mass curves space-time with stunning accuracy. We've tested them time and again, and they hold up. GPS satellites adjust for the curvature of space-time to give us accurate locations. Gravitational lensing, where light bends around massive galaxies, matches predictions from Einstein's theory. We've even detected gravitational waves, ripples in space-time from black hole collisions, just as Einstein predicted. These discoveries validate Einstein's theory over and over again. But even with all that evidence, we still don't know why mass curves space-time. We can describe how it happens, but we can't explain the mechanism. Why does space-time curve when mass is present? What is it about mass that bends the fabric of reality? The equations give us the math, but they don't tell us why. And that, in a way, is where the mystery lies. The question still exists. Why should mass curve space-time at all? It's the same story we saw with Newton. He gave us the equations for gravity, and they worked. But when asked why gravity happened, his answer was that he simply didn't know. 2 centuries later, Einstein gave us a deeper, more accurate description of gravity. But when it comes to explaining why mass curves space-time, we're still in the dark. We've reached the edge of our understanding, and we don't yet have the answer to this most fundamental question. The universe is full of questions like this, questions that push the limits of our understanding. We've made incredible strides in understanding the forces that govern our reality, but there are still things we don't know. In some ways, that's the beauty of science. It's not about having all the answers. It's about asking the right questions, exploring the unknown, and continually pushing the boundaries of our knowledge. Now, let's talk about one more mind-bending realization that comes from this new understanding of gravity. What if we could look at the entire universe not as a collection of objects interacting through forces, but as a dynamic, ever-shifting fabric? What if everything, from the smallest particles to the largest galaxies, is simply moving along the natural curves of space-time? The way we see objects falling or orbiting might be nothing more than a consequence of geometry. Every movement, every orbit, every fall is just an object following the shape of space-time. This realization reframes everything you thought you knew about the universe. You thought gravity was an invisible force pulling objects together, but it turns out gravity is just the result of objects following the natural contours of reality. And the most amazing part? We can predict these movements with incredible precision. We can use the curvature of space-time to calculate the orbits of planets, the bending of light, the movement of galaxies, all because space-time itself is bending, shifting, and changing around us. This is the power of Einstein's theory of general relativity. It shows us that what we experience as gravity isn't a force at all. It's the shape of space-time, and that shape determines everything we see and feel in the universe. The idea that gravity is just geometry completely rewrites the rules of how we understand the cosmos. Everything, from falling apples to orbiting planets, is simply moving along the geodesics of space-time, the straightest paths possible through curved reality. Now that you understand how gravity works according to Einstein's theory, let's think about the far-reaching implications of this. Gravity isn't a force pulling objects toward each other. It's the result of space-time being curved around mass. This means that every object, every planet, every star is just following the natural path dictated by the curvature of space-time. But what does this mean for us here on Earth and for everything we experience every day? Imagine you're walking down the street. You feel the ground beneath your feet, the weight pressing down on you, and you know that gravity is at work. But in this new view of the universe, what you're actually feeling is space-time pushing back on you. You're being prevented from following your natural path, your geodesic. The sensation of weight you feel isn't gravity pulling you down. It's the ground pushing back against you. You're trying to fall, to follow the curvature of space-time, but the Earth is in the way, preventing you from doing so. This understanding flips everything you thought you knew about gravity upside down. The feeling of weight that you experience is actually the result of resistance. The Earth's surface is preventing you from falling, from following your natural geodesic, your natural path through space-time. The floor beneath your feet is pushing up against you, accelerating you away from the center of the Earth. In this sense, standing still, staying where you are, requires force. Gravity's pull is simply a byproduct of space-time's curvature. It's not pulling you down, but keeping you from following the natural path that space-time would otherwise have you follow. Take astronauts on the International Space Station, for example. They're constantly in freefall around the Earth, but they don't experience gravity the way we do. They feel weightless because they are in freefall, constantly falling toward the Earth, but they're also moving sideways fast enough to miss it. So, they don't feel the gravitational pull on their bodies in the same way we do on the ground. Their natural path through space-time is unimpeded. They're simply following the curvature of space-time without anything preventing them from doing so. This is why they feel weightless. They are in freefall, moving along their geodesic, with nothing to stop them from following the natural curve of space-time. But this still leaves us with a question. Why does mass curve space-time in the first place? Why does the universe work this way? This is the question that still stumps physicists. While Einstein's equations describe how mass curves space-time with stunning accuracy, they don't tell us why. Why should mass have the ability to warp space-time? Why should the very presence of mass change the shape of reality? We know how mass does it. The equations are precise, and they work in practice. But we still don't have an answer to the underlying question of why this happens in the first place. It's a humbling realization. We've discovered a great deal about the structure of the universe, but there's still a gap in our understanding. We've figured out how space-time bends and how mass influences it, but we can't explain why mass has this ability to warp the fabric of reality. It's a mystery that remains unsolved, and for now, all we can do is continue asking the question. This is the frontier of physics, the search for a deeper understanding of the universe. And yet, even with these unanswered questions, the beauty of this picture is undeniable. The way space-time curves and bends, the way objects follow geodesics, it's not a mystery to be feared. It's a revelation about the very fabric of reality. It's the kind of truth that makes us rethink everything we thought we knew about the universe. And while we may not have all the answers, we're constantly moving closer to understanding the universe at its deepest levels. The journey isn't over. As you continue to explore the world of physics, the big questions are always there, waiting for new breakthroughs and new ways of thinking. Just like Einstein did, we must continue to ask the right questions and challenge the assumptions that limit our understanding. The universe doesn't give us easy answers. It demands that we dig deeper, look further, and embrace the mysteries that come with real understanding. In the end, what we've learned so far is just the beginning. Our understanding of gravity, space-time, and the universe is still evolving. As we ask deeper and more profound questions, the universe will continue to reveal its secrets, and with each discovery, we'll move one step closer to truly understanding the nature of reality itself. So, what does all this mean for you? The next time you drop something, or feel the weight of your body pressing down on the ground, remember, it's not gravity pulling you in some traditional way. You're simply moving along the curved path of space-time, and the Earth's surface is pushing you back, preventing you from falling. Gravity, as we once understood it, isn't a force pulling objects. It's the shape of the universe, the geometry of space-time itself, dictating the paths that objects follow. As we continue to explore the deepest mysteries of the universe, one thing is clear. The answers we seek often come from questioning the assumptions we hold. It's about looking deeper, asking the right questions, and being open to the unexpected truths that may challenge everything we thought we knew. This is the beauty of physics. It's not about easy answers. It's about uncovering the profound, the strange, and the magnificent truths hidden beneath the surface. So, stay curious, keep questioning, and always be ready to explore the unknown. The universe is waiting for you to ask the next great question.